Yeah, so, sorry again for this unplanned interruption. I will just collect the results for you simply in order to show in which direction this is going. And the long version of this will be published anyway, about 20 pages or so. We stopped with a table showing on the left-hand side typical items from the Glossar Lab, and on the right-hand side, the topos equivalent. So you can actually directly transfer one to the other. For instance, the conceptual system shows up as a category, a concept itself shows up as an object in the topos, and so on and so on. So the coherence problem, for instance, in Glossar Lab could be reframed as asking, does there exist an internal model that is an object in some topos that realizes the conceptual network as a consistent logical structure? And this corresponds in categorical terms to checking the existence of global section or of sheaf-like consistency across contexts. And I will show you this in a minute. I skip then most of the technical part, which is somewhat involved, but would certainly need quite a long time. This is simply the underpinning of what I've said so far, so it's not so. Then we come to the conclusion, which is then summarized in a mini example. And I will conclude with that mini example. What you start with are concepts, which are the vertices in the network. These concepts are A and B, which are main concepts. U1 and U2 are local concepts, such that there is an overlap. U1 cuts U2, meaning that this can be used in order to find an approximation for the concept A. So U1 and 2 are local concepts as to the main concept A, having this overlap defined, and then you have the following directed labeled relations, which are mappings, and these mappings are the isomorphisms in the topos. So they are, in terms of the diagram, they are the edges of the diagram, and you have essentially two such mappings, I1 and I2. I1 maps the local concept U1 into A, into the global concept, and U2 maps U2 into A. These embeddings are called context embeddings because you can classify, so to speak, the local concepts with respect to the greater level of the main concept. Then you have overlap projections. Projections are mappings from the overlap into U1 or U2. So I will show you that later, how that looks graphically. These are two internal projections. And the idea is to find a measure of the overlap with respect to the sharpness of definition. So in the sense, you could say that the size of the overlap is a criterion for stability of the local concepts with respect to the main concept. Then you have the main mapping, which is called R, that is the conceptual relation from A to B. So A maps to B, that are the two main concepts. And then you have U1 to B and U2 to B. These are the local concepts of A as they can map into B. And they are called the local witnesses on R as acting on U, because the structure of the mapping from A to B will be mirrored again in the structure of these two mappings S1 and S2. Now, as that is usually the case in topos theory, that looks very abstract and so on, and after a while you are mixing A's and B's, but the good point is, the nice point is that you can use it for a diagram so that it will become much clearer. Then you have equational constraints, and these are in principle the semantic and also syntactic rules. So you have what we call glossar lab identifications, namely I1 and composes P1. You see I1, that was the edge from the local concept to A, and I2 respectively, and P1 and P2 were the projections from the overlap. And this reads the composition of I1 and P1 equals the composition of I2 and P2. Or in other words, the two ways of the overlap into A agree with each other. And you have the local commutation of R, which means that R composition with I1 equals S1, and R with composition I2 equals S2. In other words, U1 and U2 are two partial descriptions of A, and they overlap along O, and the cover is defined by I1 and I2, is supposed to determine A. Determine means here determine within the acceptable range of stability of meaning. Yeah. So, and that looks much nicer now, because that is the appropriate diagram of mappings. You see A to B on top, and then you have the projections from U1, from the overlap to U1 and to U2, left and right. And you have the arrows from U1 and U2 into A. And you have the arrows from U2 and U1. I've repeated that here again, because otherwise the diagram would be a little complicated, into B. So the idea is that the left-hand side of this diagram must internally commute. A commuting diagram means that all mappings are true independent of their direction. So what you have here is, you see, you have a commutation in the sense that if you go from O to U1 and then to A, this is the same as going from O to U2 and then to A. On the other hand, going from U1 to A and then to B is the same as going from U1 to B directly, and so on. You see, so you have to find all possible paths. The path is practically giving you the semantic direction. And the syntactic rule is, of course, the equation defined, bringing the compositions together on the left and right-hand side. And if you work with these diagrams, then things look much easier, in fact. And of course, most people working in topos theory, they only work with diagrams. And in fact, they leave away all these letters. So it's perhaps not better in the end, but I can remember, by the way, just in brackets, that when I was a student at Imperial College in London, I was in the class of Abdus Salam, who was a famous particle scientist. And actually, he had the Nobel Prize in 1977. And he came always visiting us in what was called the lunch seminar. You brought your sandwiches and something to drink, and like today, and you went to the blackboard. This was the old time when there was no computer around. You had to do everything by your own hand. And so he came and he said, "Oh, I had a new idea today." And then his famous object was what we call in particle physics a scattering matrix. That is practically a sum over all interactions of particles involved. And he didn't write, he had a very large matrix on the blackboard, but he didn't enter the elements because he thought, well, everyone knew them anyway. So we were sitting somewhat not very fruitful in that sense. But this is actually a very a good point for the illustration of these abstract definitions. You have to introduce first in order to make clear what topos theory is actually about. And then you choose a base category that is a small category with the objects A, B, U1, U2, and O, and generating morphisms. They bring the dynamics in, I1, I2, P1, P2, R, S1, S2, plus, I have not listed them, all identities and composites. These are the boundary conditions, so to speak. And the relations, then, these are the so-called Parse equalities, is the quotient of a free category by the congruence generated by these equalities. That is very similar to computing with quotients such that you have a rest left and you have to take care of that rest. That is practically the direct transformation into the language of topology. So then we have what we call a Grothendieck coverage, J on C. C is our main category. And for object A, declare the family I2 and I1 and I2, as I have mentioned before, to be a covering family. Or alternatively, you can say the sieve on A generated by the I is a covering sieve. And thus, Cj is a site encoding that the local context U1 and U2 must glue to produce global data on A. You see, the point is, what you have done all the time is to define mappings and the stability of the space of free play for these mappings in order to narrow the meaning of the concept you are interested in. But you realize now, if you define it in the Grothendieck way, that this is actually the same as gluing fragments together to a global structure. And that is a topology way. You see, you transform the derivation of differential equations, so to speak, into the manipulations of topology. And that is actually what topology is all about. The pre-sheaf is then simply the mapping from the opposite of this category into the category of sets. The opposite of a category is simply the same category, but the directions of all arrows reversed. Yeah? And the sheaf condition tell you that given any elements, x1 or x2 of that pre-sheaf, that agree on a certain overlap O, there must exist a unique X with these mappings defined here. In principle, thus that you can reproduce the pullback or the push out cycle I've shown you in case of the dogs, you know. So what you do is actually to define the meaning and the narrowness of that meaning for a concept in terms of these push-outs or pullbacks in form of diagrams. And if you do all the maps that are in the composites and the identities, then you will find out that all these equalities are fulfilled, provided the example is a coherent example. So the criterion for coherence is that all possible arrows in your diagram are actually commuting. So what you have to do in practice is then to define the objects of the category, think about the adequate morphisms, writing down your diagram, and looking up whether all morphisms are commuting. And if that is the case, then all local concepts related to a global concept are coherent. So that is, of course, you will say that is quite a lot of work in principle, instead of simply defining a coherent concept. But the point is that while doing that, you have connected all the library, all the inventory of concepts you have in GlossaLab, you have connected to very important aspects of cognition and communication. And this is actually how the children learn the dogs, you know, because I mean, it looks very simple, but it's in reality, it's extremely difficult, because even in the case of dogs, you have such a variety of different dogs. So it's very difficult to classify them identically. But even when you talk in metaphors, I mean, in terms of hot dogs or dog uncles, then you realize that the child, by having learned the modus ponens of logic, of Boolean logic, has actually learned all these differences such that immediately it can point out what is in front. And this becomes more and more complicated if you think difference of a dog and a wolf or something like that, you know. So cognition of that kind does only work if you communicate it. Obviously, the children do only learn if the parents tell them. And so this is very much at the basis of all what we are doing all the time, namely to try to orient ourselves within the world in scientific terms. But in the end, this turns up as an adequate mediation of cognition and communication. Yeah, so thank you very much.
Thank you. If there is some question or comment. So maybe I have a comment. So let's say, so the clarification we are doing while we are developing one concept in GlossaLab would play the role of the communication you are meaning. So like in the communication between the child and the parent by learning what the concept means.
Yes, and the basic idea would be that behind the whole enterprise of Glossar Lab is, of course, the idea that once you have fixed the forms of discourse emerging from this construction, then you are eventually able to introduce ethical guidelines. Yeah, I mean that, you see, I mean, humans are speaking animals, you know, and I mean, they are discursive animals.
Yeah.
And if the idea is always that if the discourse is a proper discourse, then automatically, that's actually a very old idea coming from the Greek Stoa, that if you have found the adequate logic in order to express what there is, yeah, that was the old Stoic idea of physics and logic. If you can do this, then the ethics is practically an automatic result. I mean, you have nothing to do to achieve ethics, because once you have understood how to apply the appropriate logic to the world, then everything falls out by itself.
Yeah, you find what is
Yeah,
the
and of course nowadays we are not so happy anymore with this idea, because we had a lot of results we would not like to achieve, actually. But the point is that this idea is still somewhat behind all linguistic tools we develop. Yeah.
Yeah. So in other terms, the escape from logic, like somebody is trying to do, like with the post-truth, or
Yeah.
is kind of escaping from that. Huh?
Yeah, I mean, you could say, if you look for a reasonable practical application in everyday life where people do not think about topos theory or concepts or semantics, but where they use actually that in daily activities, then the best idea would be to fall back onto the logical root of the whole enterprise, especially if you can formulate it in mathematical terms, because that purifies, so to speak, your thinking from all disturbing influences which are not relevant, but which are unfortunately dominating everyday life, you know, and that is disturbing the reasonable application in practice, because you carry a load of unnecessary things around.
Okay. So I see for the issue of generalization, I see that so a good way. But one of the things we also want to investigate, to see, and to formalize is what happened with the problems of consistency. So when we have like different fields that are addressing differently, so the content. So actually, so to say, the background, what I was talking about before, the background is like those bases for the, how are they called, the push, no, how the push out,
Yeah.
for the push outs. So those basics are different in every domain, in every knowledge domain, and then so the contents are different. And how can we model that?
Yeah, the form is the same, but the contents is different. But what you have to do is to create analogies. And I mean, that is actually what is at the root of metaphorization. Yeah, that is practically analogy.
Yeah.
And I mean, if you are thinking to put as one of the main concepts the concept of information utilized in various fields, then the mechanism is the same. You have to introduce a reasonable category, and you have to check for the commutational diagrams, and then you can find an interdisciplinary path dependence, so to speak, of the concept of information in various fields.
But so the problem in a way could be say once I speak of the dog, one, so to say the concept dog in the postal, and the other speak of the dog too, which what they have in mind is actually kind of different. One of them, according to the experience, they included the ball. The others included maybe the cat, and actually, so but this is a problem that sometimes happen in scientific discourse. And then we use dog, and then so then how can we solve that?
But as I said, this is a general problem because but it's obviously functioning. I mean, you see, you hardly meet anyone who is not able to identify a dog. You see, although it's obviously not straightforward. But this is I should say, the hermeneutic nature of humans, because humans are the only species for which the world is questionable, I mean, humans are typically not taking the world as it is. They are always asking what is behind that, and of course, the reason is that in the personal communication among humans, this is the adequate strategy. Because if person A and B talk to each other, then A has always to think, well, B has said the following, but what does B mean with that? You see, because obviously persons can say the same, but obviously meaning different things. And so that is a kind of training humans have anyway. But they would like to apply this also to other fields, for instance, in physics or so. And of course, the rules are very strict. Therefore, the hermeneutic space of free play is restricted. But it works in the same way.
What is important is that the communication exists, or so the clarification.
Without communication, you can do nothing. From time to time, you meet in physics people who tell you they have found the real united theory, either by means of the Lord himself or because they are genius. But unfortunately, they cannot explain that to you because they only speak a language from another planet. And this language cannot be understood here. So then you can say, oh, well, I believe that you are a genius and you have found the key for the world. But unfortunately, it doesn't help us because you can't communicate. That is the point.
The problem sometimes is also with reality that does not manifest completely.
But
only manifest directly to say.
Yeah, but therefore, where you can say at most what reality is constituted of is when you talk in terms of mathematics, because it's an artificial language. You cannot express emotions or feelings or whatsoever with mathematics properly. But what you can do is you can find a main line of orientation which makes sure that you are living in a world you are sharing with others, And if that were not the case, then you would be lost anyway.
Okay, Thank you very much. Comment? Huh? No? So thank you. So now we have so the next speech is